talking about SDEs and things that are now on our GPUs, apparently.
Okay, so as James said, I will be talking about SDEs, but more about some practical aspects of how we can simulate these. In particular, I'll be focusing on a tool called Diffrax that by a guy called Patrick Kidger, and it's used for many things, but SDEs are like one of its pros. And recently I've been adding more methods, SDE specific methods to Diffrax, which I'm now gonna talk about. So just to maybe motivate this, I'm gonna show actually the example that Des was talking about earlier today, where you have this SDE with drift of -y⁵. Oh, sorry? Yes, I will be. Okay. Yes, it's intentional.
Just wondering if there was dropping. We could
yeah, it's
play on for people.
Yeah, wait, I'm just
Some of us are old and have terrible life.
like this. Anyway, so, and this gets unstable, as he said, sometimes when the Brownian motion gets big. And indeed, if we try to simulate it first with constant steps, right, that uses 2000 steps, but at some magic time, 17, apparently the Brownian motion is a bit too crazy and it just starts going off on a tangent out of control. But if you use adaptive steps, then somehow the solver corrects for this and manages to keep control on the sample path. And when the errors aren't too big, it manages to compensate by making bigger steps and in total makes fewer steps. And that's something that you can do with Diffrax with just a few lines of code. But now let's get to the theory of what's actually happening here. So yeah, in first part, I'll be talking about some mathematical background of all of this and how adaptive time stepping works. And then later I'll be showing just in a few lines how you can also use these tools yourself. So just to recap on notation, this is sort of the SDE that we'll be working with. Drift F, diffusion G. Now, F and G can also depend on T, but I'll write it like that. And you can imagine that one of the dimensions of Y can just be T. So we have an E-dimensional Y and a D-dimensional Brownian motion. And here I wrote it as an Ito SDE, but I'll be talking about the Tonovich SDEs as well. I won't go into what the difference is. I hope you know, but it's a slightly different rule of integration, and some solvers converge to one and some to the other. But yeah, I won't go into details on that. And we'll be dealing with strong simulation of SDEs. So Desmond said something about that, but the idea is that you fix some Brownian path, and then for that Brownian path, you produce some SDE solution which corresponds to that path. And we assume that somewhere out there, there's an actual Brownian motion path which we're following, right? Of course, we can only generate it on our computers at certain discretized, like small steps. But the idea is that we want to work on this perfect object, which we'll just sample from. Okay, and so the order of an SDE solver is gamma if its strong error, as defined by Desmond, is sort of bounded by this T by N to the gamma, where the total duration and N is the number of steps. And yeah, this is just the definition of the order as in of the strong error as in the first mini course. Okay. So as I said, we're trying to imagine that there's this mystical Brownian path somewhere out there. And because in practice, we need to somehow access this Brownian motion and hope that whatever we're simulating has some nice properties, right? I will say a few more things about how this is actually done. So first, let's talk about what adaptive time stepping is so that we know what it needs from Brownian motion, because normally how we simulate Brownian motion, that can't be used for adaptive time stepping. So let's look at what we actually need to fulfill. So you, in any sort of SDE solve, you have a solver which takes in the SDE, some Tn where you're at, Yn, and some proposed step size h hat. And then this solver produces y hat, which will be the estimation of what y should be at time Tn plus h hat. And it produces some error estimation. Now, I won't go into details, but this error can be either natively computed by the solver using an embedded method, which has its limitations, or you can use a half solver, which is essentially you take a solver which isn't able to produce an error estimation, but then you use that solver on two smaller steps and on a bigger step, and you compare the difference of the outputs to see how weird your solution is. And based on that, you estimate how bad your y hat is. And then normally with constant time stepping, you just proceed with this, increment the Tn, set Ym plus 1 to be y hat, and go on. But with adaptive, you feed this h hat and this epsilon into a controller, which then decides whether to reject or accept this step and proposes a new step size. And if it's accepted, then as with constant time stepping, you just increment your things and you go to the next step. You start up there. But if you reject, then always the new proposed step will be smaller than what you were using before, and you will restart the same step. So you won't continue, you will start again at Tn, but you'll use a smaller step size. And this is the usual control loop. Sometimes the controller can also be fed Yn, Tn, the SDE. There's all sorts of controllers, but we'll be using a PID controller, which comes from like industrial control theory, and it just cares about the current step size in the air. Okay, now, say we have a situation like this where you generated your y hat over some step, and then the controller told you, but you need to make a smaller step go back a bit. And of course, when you did your SDE solve, right, over this step, you already generated the Brownian motion W, like the increment from Tn to Tn plus hat h, right? And then your error depended on whatever your Brownian motion was at that endpoint. And so when you sample at this time, right, you can't just discard the Brownian motion from there, because usually the way errors work is if there's a big jump in the Brownian motion, then there's going to be a big error. And if you just discarded that, right, then your control loop would just cause you to have a very flat Brownian motion, which wouldn't be the right distribution, obviously, because whenever you'd make a big jump, you'd just discard it. So what we have to do is we need to condition. So say this time is S and this time is U, then you need to condition the Brownian motion that you generate here based on what you already generated, right? And you do this using a Brownian bridge. But now imagine a situation where you need to repeat this several times and do many jumps, right? Then it gets very tricky. One way to figure this out is via rejection sampling with memory. This, I think, was one of the first attempts where you can change the step size of generating your Brownian motion in any sort of way, where essentially they keep all of the times for which are ahead of you, for which you already generated the Brownian motion on a stack, and then each time you go over one, you pop it off the stack, and it's very involved, and also it's hard to do in parallel, and yeah, not easy to implement on a GPU. But for that reason, there were some other methods, which I'm gonna get to, but one more point before then. So picture how you'd usually generate Brownian motion. So the way it's usually done is like Desmond said, you have your delta t, right? And you generate delta w as root delta t times normal of 0, 1, right? Okay. And that's for each step. You just do this, right? But now the question is, so say you generate W at T1 with two streams, you fix some RNG seeds, you have the same experiment, but you repeat it 2 times. Of course, these two will be the same, right? But then in one instance, you generate W at time t, at time 2. So essentially, you have 3 times 1, 2, and 3. And here on the top, you first jump to 1, and then you jump to 2, and then you jump to 3. Whereas on the bottom one, you jump to 1, and then you jump directly to 3. And the thing is, usually, how we're generating Brownian motions, usually these ones at time 3 wouldn't be the same. But we said at the start that in order to do strong simulation and to estimate the strong order of a method, you need your Brownian path to be the same across all computations, right? But when for example, you want to check how much your precision changes when you go from step size, I don't know, 0.1 to 0.01, then if you have behavior like this, where it's not the same, then doing more steps will result in a completely different Brownian path, and then you can't match the paths to each other correctly, and you don't get the strong order, you get some sort of weak order, or even just nothing interesting. So it's good to have some sort of method which always, once you fix some seed, right, in your favorite scientific computing library, right, then you want to always get the same outputs wherever you sample in whichever order, whichever times, right? So why do you want the Brownian motion to be query independent? Because of strong ordered estimation, as I said, And for example, for training neural SDEs, where in the forward pass, you sample the Brownian motion at certain times, but then you have a method called optimize then discretize, which on the backwards pass might sample the Brownian motion at slightly different times. And if you have something where doing it at slightly different times will produce a completely different Brownian path, that's not gonna work well. And of course, you want experiment repeatability. And the methods that can enable this are either you start out with something that's extremely precise, right? And then at whichever time you sample, you will have memorized something that's close to it, and then you'll be able to recall that from memory, and you'll always just keep a bunch of pre-computed Brownian paths in memory, which has its limitations, of course, because if you're trying to do something on a GPU, right, you might only have 10, 20 gigabytes of memory, and if you want to train neural SDEs, that can become quite bad. Like, you wouldn't want just your Brownian motion to take most of your GPU memory. And then you have the Brownian interval developed by Patrick, and the virtual Brownian tree, which I'll talk more about. Now, the thing about these two is that they're not stateless, right? They need something in the memory which might keep getting updated, whereas the virtual Brownian tree only needs a seed, and otherwise there is no state, nothing to be kept in memory, which is why we chose it as the method to generate Brownian motion in Diffrax, which then enables adaptive time stepping. Okay, so this is essentially the goal of what we're trying to achieve with our Brownian motion sampling method, is that you don't just have a method of going from WT1 to WT2, right? And you're just, in most cases, you're just trying to have this transition to be of the right distribution. But what I'm saying here is that you want some function from some random seed to a whole path that has the right, that sort of matches the Wiener measure. So a Wiener measure is a measure on all continuous paths. Yeah, this is a slight typo. It should be continuous paths W, which has the property that sort of it describes the distribution of Brownian motion. And you want some sort of phi, which takes a seed, produces a path, so that if you uniformly sample your random seed, that then you get a path which is distributed according to the Wiener measure, right? So we're sampling the Brownian motion pathwise instead of step by step. And now here I say close to the Wiener measure because obviously you're doing this on a computer, so you will have some machine precision that you just can't get beyond. And also, as you know, the uniform measure on 0, 1 to the m is a discrete measure, whereas the Wiener measure is a continuous measure, but you can get very close to it. Anyway, so we use the virtual Brownian tree, which was first introduced by Lee, and was inspired by the non-virtual Brownian tree, which was introduced by Gaines and Lyons, which essentially works similarly to the Levy construction of Brownian motion. So the idea is that you first just do one interval where you just generate a Gaussian, and then you generate the Brownian motion at the half step, right? Using the Brownian bridge that I showed earlier, etc. And that converges to some Brownian motion. Now this is a very simplified version. But what we do, okay. So what we do is in each step, you have your 2 points S and U, and you know that somewhere between these two, there's some R, and you are trying to sample WR. So what you do, so yeah, you want to sample WR, and what you do is you also were provided with some random seed row. So there is something in JAX called seed splitting, which is based on a Mersenne-Twister algorithm, where you essentially use a deterministic function to split some random seed into 3 seeds, which will produce statistically independent streams of data when fed to a random number generator. So there's a whole theory about this, but the only thing you need to know is that when you call this, if this was uniform and random, then these 3 are uniformly random and independent of each other. And so how you use these? You use this row hat to generate the midpoint T. Now T is S plus U over 2. And you feed this into the Brownian bridge, you generate WT, and then you do binary search. Depending on which side of T your R is on, right? You'll either go to the left branch or the right branch, and you'll just keep. So if R is smaller than T, you'll just keep this seed. If R is bigger than T, you'll keep this seed, and you'll repeat the same process, but on just half of the interval and with one of the seeds, right? And because you have this hierarchical tree structure, right? When you have a fixed seed and a fixed R, no matter how you repeat it, you're always gonna have the same output. And because of this Brownian bridge here, this is gonna converge to the right Brownian motion. Now there's some more stuff that we do to make this exactly precise. I won't go into it, but the main idea is that in the end, when you do many of these halving steps, you also just do this sort of interpolation where you use the more general Brownian bridge to exactly evaluate R. And we also normalize the interval, but that doesn't matter. I can get more into the details of this later if there's any questions, but in any case, what we can prove about this is that the virtual Brownian tree exactly matches the pathwise joint distribution. This is a bit wordy, but essentially what you do when you call a virtual Brownian tree is you tell what sort of tolerance it has, epsilon, right? And it's gonna repeat these dyadic steps of halving the interval until the intervals are of size epsilon, and then it's gonna interpolate between these dyadic points correctly. And then essentially what this says is that if you have some set of query times R1 to Rn, such that between each Rn and Rn plus 1, there is at least one dyadic point, right? So dyadic points of this form. Then the joint distribution of all of your samples from the Brownian motion will be the same as the joint distribution of an actual Brownian motion at those times. And this can be anything, just they can't be too close together, essentially. Okay, so this is an improvement on previous implementations of the virtual Brownian tree, which didn't have this final interpolation. And those implementations were only correct if you exactly landed on one of these dyadic times, right? But in between, they just had like constant interpolation, like this. Okay. Anyway, and with this, you know that any sort of adaptive time-stepping solver will get fed the right Brownian motion, and if you repeat the procedure but with slightly different time steps, you're still gonna get the same trajectory. Okay, so the other thing that we need to unlock high order solvers for SDs is generate some integrals of Brownian motion. So what Desmond was talking about, he briefly mentioned that if you want something that has a higher order than a half, you need some sort of integral of Brownian motion. So we have just general SDs for which without some sort of Levy area, you can do at best order half. Then we have a different type of SD, which has this property that the columns of G commute in the Lie bracket. This gets technical, but the idea is that for certain types of SDs, we can do better than order half if we know some more properties of the SD. Then there's additive noise, which most SDs that are used out there seem to be additive noise, and you can achieve order 1/2 for additive noise SDs. And there's an even more special type of SD called the underdamped Lyon-Shevin diffusion, for which recently James found a third order solver, which is quite unique among SDs because, yeah, going from order half to third order is quite a difference. Yeah, so these two were found by this guy. Anyway, but here we also need some more information about the Brownian motion to be able to achieve these high orders, right? Because the Brownian motion is so weird, right? As Desmond said, you then get this root T error, right? But if you know some information about what happens between your samples of Brownian motion, then you can do better. Okay, so this can only give you order 1/2, but if you use some sort of Levy area, you can do better. So usually by Levy area, we mean space-space Levy area, which is not Gaussian, and we don't know how to sample from it exactly. It's very hard to generate, and yeah, anyway. But you have some other proxies, say, for Levy area. So other quantities that can be used to approximate this space-space Levy area. And these are the time integrals of Brownian motion. So the space-time and the space-time-time Levy areas, which are sort of related to these integrals, but they actually have a form like this. It's technical. Yeah. Anyway, if you can generate this one and this one, you can unlock the orders of convergence that I had on the previous slide. And what we did in our recent paper is we showed how you can do the virtual Brownian tree construction that I showed earlier, how you can add these two so that you can combine adaptive time stepping with high order solvers. Okay, so the reason we can do this is because this process, WHK, is Gaussian and so these are H and K. Right? This is Gaussian and Markovian, so you just need to find conditional means and covariances. It's all complicated. I'm just looking this for just to see how it looks anyway. And this allows you to do stochastic Runge-Kutta, stuff like that. I also won't delve into this, but this is mostly how all the higher order solvers are designed. If you have questions about this, I can return to this in the end. Okay. But now to some applications of this. So I mentioned the underdamped Langevin diffusion, for which we have a third order solver. Well, the interesting thing about this diffusion is that it converges to a stationary distribution. And the even more magical thing is that we don't need to know the integral of this distribution, right? So it's a stationary distribution, so its whole integral needs to be 1. But even if we don't know the whole integral, if we don't know this C, we can still use this SDE to sample from this distribution, right? And this is at the core of Markov chain Monte Carlo. It's what is needed in any sort of Bayesian inference, unnormalized Bayesian inference, etc. And the fact that we now have a third order solver which can be used adaptively for this is...
It might be e to the minus f.
Yeah,
Maybe.
maybe.
It's hard to say.
No, but there's a... Yeah, it's because there's a minus here, no? Or e to the minus... Yeah, okay.
Anyway.
Okay. Yeah, anyway, minuses. Anyway, and so an example of this is Niel's funnel. So we're sampling from this distribution. It's something we can sample from just with standard methods, right? But it's often used as a benchmark for Monte Carlo samplers, exactly because of this funnel here, because most Monte Carlo samplers sort of iterate between something which is kind of like an Euler method and something which is called metropolis adjustment. And when they get into this very narrow bit here, the metropolis adjustment sort of throws them out because it realizes, okay, we jumped somewhere here. The probability of being here is very low. So we'll just reject this step. And so many Markov chain Monte Carlo algorithms struggle with sampling from this distribution because they can't enter the funnel. Now, because we can use adaptive steps, this stops being a problem. Right? So, okay, let's decipher what's all on here. So this is the true distribution, right? We're trying to sample from this. This is what the state-of-the-art Markov chain Monte Carlo sampler does. It's called the no U-turn sampler. And as you can see, it doesn't get far into the funnel. It's okay over here, it doesn't get far. This is what happens if you run the SDE that I showed before with an Euler discretization. It's nasty. And this is with the third order solver used adaptively. As you can see, it's not exactly like the true distribution over here, but that's because of too few warm-up steps anyway. but it clearly works well in the funnel part. And then on the right, I guess, there's this convergence plot. So here I'm showing strong convergence, right? And as you can see, sort with constant steps has order 3 convergence. Euler with constant steps has order 1 convergence. Why? Didn't we just say it's order half? No, because the Langevin diffusion is very nice. And so for some SDEs, even very simple solvers like Euler have a higher convergence rate. But then there's these 2 lines, the red one and the yellow one, which are which use adaptive time stepping. Now, as you can see, adaptive time stepping uses some more evaluations, vector field evaluations, than the constant ones. Why? Because it needs more evaluations to figure out what its error is, right? So for adaptive time stepping, the solver needn't only produce the estimation for the next y, but also this epsilon, and that needs some more vector field evaluations. But even though here, the constant stepping seems better, if we look at the table up here, right? So we have sort is this third order solver. With constant time stepping, it gets big errors in the covariance, whereas the adaptive one doesn't have this issue. And this is precisely because of what I showed at the very start, instability, right? So if we have very long trajectories, there's some chance that it's gonna just shoot off, right? And that's why Euler, because it's quite unstable, some of these just shoot off and are crazy. With sort, there are very few of them, and I mean, so this is the adaptive one, but the constant one looks exactly the same. But there's some outliers which are like 10 to the 100 away, which is very bad because in any sort of Markov chain Monte Carlo application, you wouldn't know how to cut out outliers. You might have a very weird probability landscape, and you just want something that is stable, and you don't have to worry about what's shooting off where. And that's why it's worth having a few more vector evaluations, vector field evaluations, or just having the certainty that your solver will never overshoot randomly. Okay, so now a bit about how this all fits into the scientific computing framework out there. So you all probably know what NumPy is, and maybe many of you heard about JAX. It's a way to essentially put NumPy on the GPU. It uses in the background XLA, which is sort of the lower end of, used to be first used for TensorFlow, but TensorFlow has a clunky UI, so Google made JAX to sort of bring XLA to the nice and widely used UI of NumPy. So because all of JAX looks pretty much like NumPy, I'm sure anyone who's familiar with NumPy will find it, at least the basic stuff in JAX, very easy to use. And it enables GPU acceleration of whatever you're doing in NumPy. And it also has very easy to use automatic differentiation. And now inside JAX, Patrick built Diffrax, which deals with various ODE, SD, and CD solvers. CDs stand for controlled differential equations, and it's also one of the go-to tools for neural differential equations, whether they be ODs, SDs, or CDs, and it also supports adaptive time stepping. Okay, so now I'm gonna show how this can be used in just a few lines of code. If you want, you can take a picture of this. I'll show the notebook here, but yeah, for now, many of these things are still only in my repository, but they're slowly making their way into the actual Diffrax package. I mean, many SRKs are already in there. Anyway, this is where you can find this notebook for sort of guidance on how to use these things. But it's all also gonna be in the documentation for Diffrax. Okay, so let's get to it. Okay, so I'm gonna show how to simulate an SDE. Sorry, this is so small. I don't know how to make this part bigger. I'm gonna show how to simulate an SDE of this form. It's just some SDE that I randomly came up with, and we know nothing about it. No theoretical results about it, but somehow through the magic of JAX, we'll be able to play with it in various interesting ways. And one thing to note is it's a Stratonovich SDE. The reason for that is that the solver we'll be using converges to the Stratonovich solution. There's more explained about this difference and which solvers converge to which later in the notebook, but I won't be covering this. So the way to define an SDE in Diffrax, you just need to define F and G, and they need to have a special form, right? They need to take 3 arguments, T, Y, and args. So args are just some parameters of the SDE. Here we have like an SDE that's parameterized by 3 things, an alpha, a beta, and a gamma. And this can also be empty. You don't need to have any args. But yeah, this is just to something that, for example, into args you'd put in a neural SDE, your args would be the neural network. Okay. And so here, what we put, so we said F is alpha minus beta y. So this will just be alpha minus, right? And this is all you need. And then this will be multiplied by dt, right? And then you have the diffusion, which here, this is a matrix. So it needs to be a 3x2 matrix because we're using 3-dimensional y and the 2-dimensional Brownian motion. And the important thing here is to realize which way the shape is, but you'll be able to see this here in the notebook. Anyway, and then you need to also define the y0, which is just, you can, so one thing to note, I'm using JMP to stand for jax.numpy. And all of the commands that are in NumPy are usually also in jax.numpy, and you use them in exactly the same way. So it's gonna be familiar to you. Okay. And then we just need to specify the parameters and the time domain. Okay. Now, to solve the SDE, right, we still need to package all of the information that we had here, so F and G and the starting position, into terms. So Diffrax uses, for SDEs, you'll use two types of terms. You'll use the ODE terms, which is the drift part, and you'll use the control term, which is the stochastic part. And into the control term fits the G and the Brownian motion. You define a Brownian motion like this. I'm not gonna dwell on these things too much. It's all online. It's also all in the documentation. It's just mostly to show that it's quite simple. And then you put these two terms into a multi-term, which is just a sum of two terms. And then you specify the your step size. And what does all the magic is this function Diffrax solve, right? Where you feed the terms, you put in the solver. Spark is one of the new stochastic Runge-Kutta methods devised by James. And you fill in all the other important information. And you also want to put in at which times you want the solution to be saved, right? And then we just plot it, right? So here below are the 2 dimensions of Brownian motion, and above is the SDE trajectory, right? Now, using adaptive time stepping is very easy. What we need is all the setup remains the same. We just need this controller. There are several types of controller that you can have, but the most widely used one is the PID controller, right? And you keep everything in Diffrax solve the same, except you just add the controller, and you add the max number of steps. So this is usually set to 2 to the 13, but sometimes you need more. And then if you're trying to compute your solver orders, you might want to check how many steps your solver used, right? Because you don't know, it's adaptive. It might go very precise on you and take a very long time. But anyway, this is what we get. And here in the bottom graph, I plotted how many steps it took in each time bin, right? And as you can see, where the solution gets more jagged, right, it's using more steps. This is because if you saw in the definition of the SDE, we were using a diffusion to have a bigger variance as time increases. Okay. Now another important thing is the half solver. So I mentioned before that some solvers can produce error estimates using an embedded method, whereas some don't. So for example, General Shark is a similar method to Spark that we were using before. The main difference is that Spark uses one more vector field evaluation. So it's slower if you're not interested in an error estimation, but Shark is faster because of fewer evaluations, but it can't produce an error estimate. So you'll need to wrap it in this half solver, and then everything else is the same, right? So below there's a table of all the solvers. Some have an embedded method, some don't. If they don't have an embedded method, you need to wrap them in a half solver to be used adaptively. And this produces slightly different stuff. So the density plot before was different. The solution, of course, looks pretty much the same. But also, as you can see, this uses fewer steps. Why? Because a half solver is actually a much better way to estimate errors. I can say more about this later, but yeah, there's, I guess, some usually in OD simulation, people like to use embedded methods, but there are theoretical reasons why they don't actually give you the right error estimation. Like the error estimation can be completely different from what your error actually is, but in practice, they usually work well. Okay, now we want to go towards the more fancy things that JAX can do. So for example, we want to run this same SDE for many Brownian paths. So for example, if we're trying to estimate some function or an expectation of some function, right? We want to take this expectation of over many Brownian paths, right? We want to use the same sort of procedure, but we will VMAP over it. So what we have here, right, is we have the same thing as before, except that we have it all in a function and we'll VMAP over the random keys. So these are the keys, the rows that are fed into the virtual Brownian tree here, right? And we sort of will take this function and we'll compute it for many keys, which will be randomly chosen, and then we'll take an expectation over those keys, right? And to do that, what you need is just at jax.vmap. And that's all. And then to produce your keys is you just do this. And that will produce many solutions of the SDE, right? So 100 of them. And then once we have this whole batch of samples, right, we can think, okay, what if we want to optimize the parameters of an SDE so that it matches a certain variance and mean, right? So we will optimize to get a mean of 0, 1, 0 and just a variance of 2 at time t is 2, right? So normally we don't know anything about this SDE, no theoretical guarantees, so we couldn't do this with theory. So we need to do it numerically. And the good thing about JAX and the way Diffrax is written is you can just do auto differentiation through an SDE solve. And I won't go into the details of what is happening here, but essentially you just define a loss. And then here in this, you can use a magical function, jax.value and, jax.value and grad, which just automatically differentiates your whole SDE solve, right? Everything that we are doing now, it goes back, it looks how the outputs are influenced by the parameters alpha, beta, and gamma, and optimizes it, and the loss goes down, and you find the right parameters, and then you see that now the mean and the variance match what we wanted, whereas before at the start they were like just all over the place. And then we can also visualize this SDE. It looks kind of similar, but also clearly it tends to 0 at the end. I don't know. Anyway, and here at the very end, we also have, well, something that won't show up correctly now, but Okay. Yeah, I was doing the right thing. Yeah, so table of all the various solvers in Diffrax. So yeah, that's it for my part. This is all up on my GitHub, and many of these solvers are already in. So all of these ones are already in Diffrax. The third order solvers are not in Diffrax yet, but they're getting there. And yeah, you can use them adaptively. You can use them on your GPU. They're very fast and they converge quickly. So yeah, good for training neural SDEs, I suppose.
Are there any questions?